So for additional session, if you want, take a look at my calendar this week, next week. If you want, you can just give me 2-3 options and then talk with Akshay when this room is available and let me know. Okay, or you can have TAs run additional session. Okay, so what we did in the previous class, I'll recap in the next 2-3 minutes, and there were a few questions that I did not answer based on your minute papers, the questions that you had asked. So I'll go over them. Okay, so what we are doing in this particular module is looking at solid catalyzed reactions and see what reactions are taking place at the molecular level. The solid catalyzed reactions never take place as a single step. They are always, solid catalyzed reactions are not elementary. Those take place in multiple steps. The multiple steps that constitute a reaction mechanism are something that's a topic of a separate discussion. Okay. But let us say that we have postulated a mechanism, we have postulated some assumptions about the particular mechanism. How do we derive a rate law from the mechanism that we can then use, we can then analyze, then we can draw some inferences based on that, or we can design a system based on that. Okay, that is the purpose of the overall process. The purpose of this particular module is how do you go from a mechanism to a rate law, to a rate expression based on certain concepts. Okay. Now, we talked about where all are solid catalyzed reactions used. We talked about what are the various processes that are happening in any solid reaction that is taking place. There is external diffusion, there is diffusion within the pores, there is reaction on the surface of the the active catalyst. Okay. Those reactions typically involve multiple steps. The most common steps are adsorption, surface reaction and desorption steps. The standard adsorption is monolayer adsorption, and that is called Langmuir adsorption, and the reason why it is called Langmuir adsorption is because it follows certain postulates, and those postulates are based on monolayer adsorption 1, okay, and that is the reason why we could use this particular reaction as, okay, that is the reason why we could use this particular reaction as a single reaction that is taking place with one site, and once the entire site gets covered, we are not talking about a second layer and a third layer of adsorption. We are only talking about monolayer adsorption. That is one. The second assumption, which again we have not talked about specifically, but it will be there in your adsorption course. I think this semester or next semester, I don't know, but that is being taught in your adsorption course, and the assumption over there is that irrespective of what site we are talking about, right, it is, if it is a particular site and a particular species that is adsorbing on that site, whether it is first molecule that is adsorbing or whether it is the last molecule in the on the monolayer that is adsorbing, the energetics of that adsorption, free energy as well as enthalpy of that adsorption remains exactly the same. That is an assumption, that is not necessarily always correct, because there are going to be interactions when more species are adsorbed on the surface, but that is a reasonable approximation for a lot of surfaces that we are looking at. Okay. So, those were the assumptions in Langmuir adsorption, and the way the Langmuir adsorption behaves is it is a monolayer adsorption and it has this kind of a saturation behavior. Okay. When the surface is completely empty, at that time the adsorption is first order. When surface is nearly completely filled, the adsorption is approximately 0 order. That means not 0 order, the adsorption saturates. Okay. So, that is the behavior of monolayer adsorption. Before we did that, we went over certain terminologies, concentration of the species on the surface and its surface coverages, and then we took up examples and we talked about how concentration is related to the surfaces. Okay. We talked about a very generic mechanism, A going to P, other generic mechanisms are A plus B going to P, A going to P plus Q or A plus B going to P plus Q, which covers about 2/3 of or maybe 3/4 of the most common reactions that you will encounter as chemical engineers or as catalysis technology practitioners. Okay. And then we took the example of ammonia and we looked at one particular adsorption, that is adsorption, the molecular adsorption of ammonia. Okay. Now, there was one question, is PE applicable only when there are multiple reactions? Any thoughts? What about this case? Are there multiple reactions? No. Let us say we were interested in capture of ammonia. Let us say there is small amounts of ammonia that is emitted. You can take an acidic adsorbate and you can capture ammonia on an acidic adsorbate, in which case this is the only reaction that will take place. Okay. So, the reaction okay, R net is R forward minus R backward, which is equal to K1 okay. At equilibrium this is 0. At partial equilibrium this is not 0, what it means is K1 is very large. Okay. So, the net rate of reaction might be large because K1 is large and this is far from equilibrium, or R net can be large because K1 is extremely large and this one is extremely small. Okay. So, you are really going, let us say you are doing a tug of war with 100 people on each side. Okay. So, 100 people on one side and 99 people on the other side, right, and that 100 people are winning. Okay. But the forward power is very well matched with the backward power, even though all of you are moving at one particular direction. The forward power and backward power is given by this part, the coefficient. Okay. And how much you will be able to move is given by 100 minus 99 mismatch. Okay. So, please understand this particular aspect. The difference between equilibrium and partial equilibrium, equilibrium this is 0, partial equilibrium this quantity is much smaller than this quantity. Okay. That is what partial equilibrium means. Okay. Again, when it comes to this particular course, it will be unambiguous whether it is partial equilibrium or not. When it comes to research, you need to take a decision. Okay. How do you decide whether something is in partial equilibrium? R forward divided by R backward, something that you yourself were able to say. How close is it, sorry, R forward to divided by this, approximately equal to 0.5. Okay. Some people will say approximately equal to 0.5 would be 0.49 to 0.51, some people might say 0.45 to 0.55. Okay. One case it is 1%, another case it is 10%, but not more than that. Okay. So, the answer to the question, does partial equilibrium imply that there need to be multiple reactions? No. Until the previous lecture, we had all examples that we had considered, that was one reaction out of multiple reactions was in partial equilibrium, but that is not a requirement for this concept of partial equilibrium. It can very well be one particular reaction in partial equilibrium. Okay. The another interesting thing is if you take this particular reaction and do pseudo steady state on NH3, we will get the same result. Okay. So, if it is only one reaction, pseudo steady state as well as partial equilibrium will give you the same result. Okay. Okay. Now, there was another question about can we go over the idea of Kp, Kc and so on. So, let us again you can take any reaction, but let us take N2 plus. Okay, if we were to write this as half N2 plus 3 by 2 H2 going to 1 NH3, our delta G will be just half of that. Okay, and because it is e to the power and so on, the ratios will just be square root of that. Okay, so when we are talking about equilibrium and the delta G with the reaction, it is as the reaction is written. So, just because I gave you delta G of this as say 90 kilojoules, do not rewrite this reaction as half and keep the same delta G. You cannot do that. If you do that, then the delta G has to be scaled appropriately. Delta G is a state function. Okay. All right. So, let us say that at equilibrium, we have Pn2 equal to 0.5 bar, I do not know why I took those values, but let us say this is at equilibrium. Okay. What is your value of Kp? Can you calculate this? Yeah. 3-4 minutes to calculate. The definition of Kp, yes, anyone value? 36. 36 what? The answer is still incomplete. Bar to the power -2. What if you are calculating your Kp in terms of pascals? Right? How did you get it? You got it by okay. So Ka is a function of P by P naught. P naught is 1 bar. Okay. So, if we were using in calculation in bar, K equilibrium is going to be what's the units? What's the units? Bar? No, right? It's dimensionless. Okay. Why? Bar and bar over here got cancelled. Bar over here got cancelled. Let us do the calculation in pascals. Okay. What is P0 of NH3 in pascals when you are doing this calculation in pascals? What's the pressure of NH3 in pascals? 1.5 10 to the power 5. What is 1 bar pressure in pascals? Oh, 10 power 5. So, if we were to do the calculation in pascals, what are the units here? Again dimensionless. Okay. See this value and this value, they are the same. This value and this value, they are different. See this value, compare this value and this value. Are the numbers the same? Yes, but is Kp equal to K equilibrium? No, why not? Because K equilibrium is dimensionless, Kp is not dimensionless. Okay. So, now you understand what I mean by shortcut, but that is not the truth. So, if you were to calculate your Kp in bar units, the value that you will get will be numerically the same as the value that you will get for K equilibrium, but Kp is not dimensionless. The only time Kp will be dimensionless is when the number of reactants is equal to number of products. Okay. For example, water gas shift. If it is not, if it is a reaction like ammonia synthesis, it will not be dimensionless. Okay. Clear? Okay. So, when we say that K equal to e to the power minus delta G by RT, we are talking about this K. Okay. You cannot, so one of the questions also was, these are thermodynamic concept. No, this is reality, or this is what we know about the reality, or what is postulated to be our understanding of reality, supported by a lot of mathematical formulations and huge amount of experimental results, not one of which contradict that postulate or that hypothesis. That is when that hypothesis becomes a theory. Okay. What is the difference between theory and a law? Law is something that is explaining the observation. Theory is something that explains the observation and there is a mathematical, molecular or submolecular level backing to it. Okay. First law, second law and so on are basically something that we have observed, and we have yet to find a single case that violates the 0th, first and second and third laws. Okay. So, these is what we know about reality as we have observed in so many 100 years. Okay. We have bucketed them as thermodynamics and reaction engineering and so on, so that for our convenience of understanding. Okay. So, at this level you can't come and, or neither can you, neither can I come and say that, oh, this is not thermodynamics, what can I do about it? No, you can't. Okay. So, this is a time when ideas from thermodynamics or mass transfer or heat transfer or the transport and reaction engineering are all you have to look at as a holistic set of tools that you can use, and so also AI and this and that, these are all sets of tools. They are not realities. Okay. These are tools that we use in order to understand the reality, in order to use that understanding, in order to improve the processes and make them better, make them more efficient, make them more sustainable, make them whatever else you might have. Okay. Alright. So, that is that. So, those were, as far as I could see, the more critical questions. The other thing that I already said, some people have requested once in maybe 2 weeks we can have some kind of a session where we go over doubt solving, problem solving, whatever. And as I said earlier, please let me know, schedule it something in the evening so that we can run more than 1 hour if needed. Okay. So, let us get on to the next case, dissociative adsorption. Write down partial equilibrium and express theta H star in terms of theta star and partial pressure of H2. Okay. This is where there is going to be certain amount of confusion. Remember the definition of partial equilibrium, it is based on the reactions small rf and small rb, not capital R. Stoichiometry does not feature in small r. You do not have to look at the board and copy it down. This will be available to you on the site, right. Do it yourself and see where you are getting confused. Okay. One point of confusion for several students is, let us say we were to just take an irreversible reaction. Okay. should it not be 2k1 ph2 p star square? Should it be this or should it be k1 ph2 p star squared? I do not know whether the confusion is because you are actually confused or confusion is because me asking a question means you are feeling I might be putting a googly. So, I am not Anil Kumble or whatever, and I do not watch cricket much, so I do not know who the today's cricketers are. Last I watched cricket was my student days. Okay. So, this is the rate of formation of H star. Okay. Remember, R okay. So, okay. Again, please do not jot down things that are there on this, write down things that will help you understand the material, okay, which could even be, this is waste of time, I understand it already. So, when you take that and you take this particular slide together, you will hopefully understand it. Okay. So, what if there were two species that were being adsorbed? How do you handle this? Assuming both the reactions were in partial equilibrium. Okay. What do you get if the first reaction was in partial equilibrium? You write it down, I will write down over here what you get if the second reaction was in partial equilibrium. Okay, what does theta star mean? Let us say A is hydrogen, in this particular picture. What is theta star? Value of theta star 1 by 2, 3 by 6. What is the value of theta h star? 2 by 6 or 1 by 3? What is the value of theta nh3 star? 1 by 6. Okay. So, theta h star is the fraction of the total sites that are covered by atomic hydrogen. Theta nh3 star is the fraction of the total active sites that are covered by molecular ammonia. Theta star is fraction of the available sites that are as of now uncovered. Okay. I do not know if that was your question or not. Was that your question? Okay. Okay. One is the sum of all of the covered sites and uncovered sites. So, that will always be equal to 1, theta star plus theta n star plus theta h star plus theta nh3 star plus whatever else. Okay. Okay. We are showing this as a picture that is very static. In reality, things are not static, things are moving around, things are jumping around. Right now, A might be on this particular site, literally nanoseconds later A might be go on to this site, few nanoseconds later A might end up going on this site. Okay, it will adsorb, desorb, this A might go on into the gas phase, again come back onto the surface. Okay, it might migrate, physically migrate on the surface. It can hop on onto surface. Migration is basically go from one side to another almost. So, think of it like you are sleeping on the road and rolling on the road. That's the surface migration. Hopping is basically you are standing on the road and jumping. Okay, desorption, it will go back into the gas phase. All of these things are happening simultaneously. Everything is happening simultaneously. So, the picture that we are showing is kind of a snapshot for our analysis. If things are not moving around, when things will not move around on the surface, literally the only time it will not move around at the surface is when the temperature is 0 Kelvin. Anything other than 0 Kelvin, there will be movement. Okay, at 5 Kelvin for example, the movement will be very slow to be even detectable, but there will be movement. The only time when things won't move is at 0 Kelvin. Okay, that's the definition of 0 Kelvin. Okay, clear? What if there are 3 adsorbed species? You know what the procedure that you will do, right? Assuming all 3 are in partial equilibrium, I hope you know the procedure that you will adopt. Let us talk about shortcut that you would adopt. What is going to be theta nh3 star? Numerator K1 or KNH3, does not matter. Okay, over here purposely I have put K1 over here and KNH3 and KH2 over here. Okay, notations are for our convenience, that is all. I mean, right now I have put this reaction as first, this reaction as second. Tomorrow I might have ended up switching it. Just because they are switched physically, they do not change. That is why over here I have used KNH3, K and KH2, and because we are talking about snapshot of what I am showing over here, I have used K1 and K2. Okay, this is not a mistake. This is just to tell you that, you know, yeah, sign conventions and conventions are for our convenience. So, what is going to be the denominator? What is going to be the form of the denominator? Pattern matching. Will there be 1? 1 plus? Where physically, where does this 1 come from? Total side balance. What is the next item? K1 PNH3. Where does this come from? The ones that are covered by ammonia. Plus, what else will come? Why under root? Some people have said under root. Why? Because it is dissociative adsorption. Plus under root. What if we were to add one more reaction over here? Okay, what is the difference between this guy and this guy? Yeah, so N2 has dissociated and nitrogen atom is sitting on the surface. The second, the blue example is where N2 has not dissociated and a molecular nitrogen, or as chemists will say, dinitrogen species is sitting on the surface. Okay, there are two different species sitting on the surface. If there are two different species sitting on the surface, that additional term will come in and that term will become K4 PN2 square root, no square root. Okay. Again, let me erase this, we do not want to unnecessarily complicate things. Okay. This is what we are going to get. Okay. We will introduce the next concept. Most abundant reactive intermediate. Okay. Let us say that through some surface science experiments, showed us that the only species that are covering the surface, or the only species that is covering the surface is hydrogen. Okay. What do you mean when you hear the word hydrogen is the only adsorbed species? Does it mean ammonia is not adsorbed, nitrogen is not adsorbed? It does not mean that ammonia and nitrogen are not adsorbed. It just means that the coverage of hydrogen is at least 3 orders of magnitude more than ammonia and nitrogen. That means if hydrogen coverage is say 0.5, 0.6, 0.7, nitrogen and ammonia coverage is less than 10 to the power minus 3 or 10 to the power minus 4. Okay, does not mean that those coverages are not important. It just means that when it comes into this denominator, those effects do not play a role. Those effects will play a role in the numerator if they appear, will not play a role in the denominator. Okay, remember why? Because it is 1 plus alpha A plus beta B plus gamma C plus delta D. Okay, so in relation with 1, beta B, gamma C, delta D are 0. In relationship with 1, alpha A is not 0. Okay, look at what is there in the numerator. There is no 1 plus blah blah blah. Okay, so you cannot eliminate this guy because it is very small, but you can eliminate this guy because it is small. Okay, so if H star is the only adsorbed species, then 1 is much greater than okay. Compare this and this, we have not gotten rid of the numerator, we have gotten rid of that same term in the denominator. If that term was 0, we will get rid of it in both numerator and denominator. That term is not 0, it is 0 in comparison with 1. There is a difference between the two. Okay. So, we have talked about 3 approximations. The 3 approximations are partial equilibrium. Okay. Beginning of the class I also said that ammonia, if it is a single adsorbed species, you could even say that ammonia is under pseudo steady state condition. Okay. So, pseudo steady state, partial equilibrium are 2 approximations, and the third approximation that I have introduced right now is most abundant reactive intermediate. Most abundant reactive intermediate does not feature into this equation. The most abundant reactive intermediate features into this equation. Okay, that is why it goes into the denominator and not in the numerator. Okay. So, just to recap what we have said so far, N2 adsorption, the rate of adsorption can be written in this form, okay, K forward minus K backward, and yeah. So, this I have just rewritten again in the summary slide over here, but in concentration terms instead of partial pressure terms. Okay. So, likewise hydrogen adsorption, likewise ammonia desorption or adsorption. Okay. K dash NH3 is nothing but 1 by K NH3. So, if it was K NH3, it will come in the numerator in the desorption reaction. Okay. That is all this particular slide is saying, it is just summarizing all the things that we have done so far. Okay. For the consistency of notations, I will use capital Kx to represent adsorption of X, capital K1 to represent as the reaction is written. Okay. That is the reason why over here I have used these two replaceably. Okay. K1 is equal to KNH3, K2 is equal to KH2 as written. Okay. If I have written it as a desorption step, K of the desorption reaction will be 1 by Kx. Okay. Partial equilibrium assumption, this term in the bracket is approximately 0. Okay. As I had said earlier, it does not mean this is approximately 0, it means that the K1 is very large, in comparison with that this particular value is very small. Okay. All that it means is K1 is very large. Okay. The example of 100 people pulling over here, 99 people pulling over there. Okay. None of them is Bahubali, they are all equally strong. Okay. The next class we are going to talk about what if you have surface reactions also coming into picture, how do you do Langmuir-Hinshelwood models. Okay. Surface reactions are of 3 types. Okay. One is surface reactions involving a single adsorbed species, another is surface reactions involving 2 adsorbed species, and the third one is surface reaction involving a gas phase species with an adsorbed species. Okay. There is a fourth thing also that comes in, that is called Mars-Van Krevelen. Okay. When this particular adsorbed species is a lattice species, okay, not an add atom, it is a lattice species. Again, if you have first time you are hearing that term, forget what I said in the last 15 seconds. Okay. There are a couple of people in catalysis who have a little bit of catalysis background perhaps, so that this particular term might be relevant to you. Okay. As far as we are concerned, the 3 types of reactions that we are going to look at is A star going to product, A star plus B star going to products, okay, and A gas plus B star going to product. Okay. So, this is not adsorption. Okay. Adsorption will be CO plus star giving CO star, that we have already done. What we are going to do in the next lecture is to look at surface reaction steps. Okay. This is the slide that we will start off in the next lecture. Okay. Thanks and see you in the next lecture.